When I was a little girl, I got lost in the jungle. I heard the ocean in the distance, somewhere far away. The sound of the waves carried me out of the trees, out of the darkness, to safety. We talk a lot about the things we see, but what we hear can guide us, comfort us, even amaze us. My name is Lucia, and I'm getting a PhD in physics. Well, I'm hoping to get a PhD in physics anytime now. If I've learned anything in the last few years, it's that things are not as simple as we think. The ocean can seem calm and tranquil, gently changing with the tides. But the ocean can be violent. Waves can churn under the surface in intricate and complex ways. Even simple things are more complex than we thought, like the way gravity keeps us grounded. Since the time of Newton, we have thought of gravity as a force pulling objects toward Earth. Check this out. But then in grad school, they taught us that Einstein described gravity as more like the ocean. Dark, complex, mysterious. Just like the ocean, gravity can churn violently. And like a drop in the ocean, gravity can become a wave. My advisor and I are researching extreme gravity and gravitational waves. Gravitational waves have a story to tell about the most extreme systems in the universe. This story is so complex that it can only be understood using complicated mathematics and computer simulations. Imagine colliding neutron stars, merging black holes, giant exploding stars. For the first time, we can listen to these amazing stories. Einstein wrote the equations that describe gravity as we understand it today. Between 1905 and 1915, Einstein created his masterpiece, the theory of general relativity. The cornerstone of this theory is that space and time form a continuum called space-time. Space-time can stretch and curve due to the presence of dense objects like planets or stars. Gravity, to Einstein, was not a force as Newton imagined. Rather, it was a result of the curvature of space-time. If this were true, Einstein reasoned, then space-time could also vibrate and undulate. Like when an object falls into water, there are ripples created on the surface. Gravitational waves are ripples in gravity itself. How do we know Einstein's theory is true? In 100 years of testing Einstein's theory, scientists have yet to find one experiment that disagrees with the predictions of his masterpiece. Not even one. How crazy is that? I have a cool example. For years, scientists were confused about the orbit of Mercury. All the planets in our solar system move in ellipses around the sun, but Mercury's orbit is crazy elliptical with a little wobble thrown in. We call that wobble precession. Here's how Einstein's theory of spacetime can explain Mercury's strange orbit. The sun is so massive that it curves spacetime a lot. Since Mercury is the closest planet to the sun, its orbit is the most affected. In one of my grad classes, we calculated the orbit of Mercury using Einstein's theory of general relativity. We learned that it is the curvature of spacetime created by the sun that causes Mercury's wobbly orbit. Einstein's theory also predicts other effects. If spacetime is really curved, then light should follow a curved path as it travels from distant stars to Earth. And if the sun was between Earth and the stars, stay with me here, then the starlight would have to bend around the sun before reaching us, right? Einstein made a prediction this would happen. Not only that, he calculated exactly how much the light would bend. And this was before anybody observed this effect. In 1919, Einstein's light-bending prediction was confirmed by a team led by English royal astronomer Sir Arthur Eddington. Here is what happened. During a solar eclipse, Eddington photographed stars very close to the sun. Those are here. Six months later, when the sun was not between Earth and the stars, Eddington photographed the same stars again. Without the sun bending space-time, those same stars appeared here. The stars were not in the same place. It is as if the stars had moved a vast distance in the 6 months between observations. That's impossible. It must have been starlight bending during the first observation and not during the second. In other words, Eddington found exactly the effect that Einstein predicted. Experiments and observations were telling us that Einstein was right. Space-time bends and curves significantly around massive objects like stars. Wait a second. Okay, that's better. So that's why the light produced by this star looks like a ring instead of a point. Light is bending on its way to Earth. Scientists from all around the world started to use Einstein's theory to make amazing discoveries. Here's a great example. Using Einstein's formulas, scientists reasoned that if an object in space is really dense, it will collapse onto itself and become a new type of star, a dark star, a black hole. Imagine if you took the sun, which could fit 1.3 million Earths inside it, and compressed it down to the size of 32 football fields. That would create a black hole. The curvature of space-time, gravity, is so strong in a black hole that nothing, not even light, can escape. I like to think of black holes as the corpses of dead stars that shine no more. I know, very poetic of me. When two black holes collide, space-time is forced to undulate and vibrate. Waves are formed and propagate away from the black hole at the speed of light. These are gravitational waves. And they are produced at other times too. Like when stars explode in amazing supernova. Or when neutron stars collide and produce short bursts of radiation. These gravitational waves fill Einstein's universe in a quiet symphony of incredible activity and dynamic range. Einstein's theory predicted the existence of gravitational waves. And 100 years later, the detection of gravitational waves by advanced LIGO is one more confirmation that Einstein was right all along. Gravitational waves help us answer some huge questions, like how do stars die? How are black holes born? Gravitational waves paint a whole new picture of our universe. But here's an interesting thing. It is a picture that we cannot see. Gravitational waves are not light waves, so we can't just point a telescope to observe them. We don't see gravitational waves. We hear them. But how? We use special equipment to amplify the waves. That is what you are listening to right now. This is the sound of colliding neutron stars. This is the sound of merging black holes. And this is the sound when you add music. Detecting them is more complicated than hearing ocean waves. Here's how we do it. Scientists built two intersecting tunnels with mirrors at the ends. They shoot lasers down the tunnels, bounce them off the mirrors, then let the laser light recombine. When a gravitational wave is passing through Earth, the wave stretches one tunnel and compresses the other. When that happens, the lasers get out of phase. They don't line up when they recombine. These laser interferometers are antenna listening stations for gravitational waves. There are several sites like this around the world. Now imagine these listening stations in space. Scientists plan to launch a laser interferometer antenna into space to expand our understanding of gravitational waves. Scientists from the European Space Agency and NASA are leading the mission. Years of experience launching rockets and satellites will help guide these efforts. By using powerful lasers and other tools to detect gravitational waves, we can continue to listen to the symphony of the universe. When I was a little girl, the sound of the ocean led me out of the jungle. Hearing can be just as important as seeing. There are things in the universe we cannot see. We cannot see black holes, but we have strong evidence they are there. We can hear the gravitational waves black holes produce when they collide with each other. The universe is becoming audible. These sounds can give us a new understanding of how the universe was formed and how it continues to change. The waves tell an unseen story, but we don't know how the story will end. Observing gravitational waves will lead to discoveries and technologies that we can only dream about. Let's close our eyes. Imagine our future. And listen.
5, 4, 3, 2, 1, 0, and liftoff.
Temperature rising in all 6 ground locutors. Good chamber pressure on the main engine. Good chamber pressure on both verniers. Good chamber pressure on all 6 groundlet motors. 20 seconds into the flight. 29 seconds, Mach 1, vehicle now going transonic. 35 seconds in.